Hey guys, so I'm going to try something that's new to me today. I'm going to walk you through an exam question from a physics undergraduate paper that I sat a few years ago now. And this particular question is on Newtonian mechanics, so we have balls rolling here it looks like. And I'm going to try and show you exactly what the examiner wants from you in this question and how to get the most marks out of it. So I would recommend that you maybe pause the video for a few moments and read through the question, maybe even try it yourself before you follow me through. But definitely just take a look at it, familiarize yourself with the question so you understand exactly what we're doing here today. Now, with that said, let's just jump right into this question. We'll start with 1a, and it says, a ball starts its motion from the top of a frictionless incline of length L equals 25 meters. The initial velocity of the ball is v0 equals 0 meters per second, and the velocity of the ball at the bottom of the incline is v equals 10 meters per second. Find the angle theta of the incline. So here we are, we're on question A, and it's always a good idea to start with a picture of what we're dealing with. So let's get one of these going now. Here's our incline, and it's at an angle theta. And our ball, let's make our ball red. It starts up here with v0, this is its velocity, 0 meters per second. And then it finishes off at the bottom of the incline after rolling down with v equals 10 meters per second. And what else do we know here? We know that our incline, our slope, is of length L equals 25 meters. So immediately we can see that it's useful to draw a picture here because now we know we're dealing with a right angled triangle. So we know that if we find this height, the height of the ball here, h, we can use trigonometry to find this angle because we have the length of the slope, we have our L, and we have a h. So they're just the sine of the angle, right? And to do this, to find this h, there's a couple of ways. You could use equations of motion and try and find the acceleration of this ball, but we're going to use energy conservation because personally I think it's easier. I think once you understand how to use energy conservation, it works in all situations and it's a beautiful way of doing things. So let's start by considering the energy of our ball at the top of the slope. So the total energy of our ball, initial energy, EI, is equal to its potential energy, which is just mgh, where m is the mass of our ball, g is the gravitational constant, and h is this height here that we don't know. So it's the potential energy plus the kinetic energy of the ball, which is half m, the mass again, times v0 squared. And our v0 is 0 meters per second, so we can discount our kinetic energy because it's 0. So we're just multiplying through by this v0 here. So our initial energy is simply mgh. And then our energy after the ball has rolled down our incline, the energy of this ball afterwards, EF, is the same again. It's the potential mgh f, where hf is the height that the ball finishes at, plus half m v squared, where v now is our 10 meters per second. And conveniently we can cancel another term here, because our final h, the height of this ball at the end is 0, right? It's at ground level. It has no height. So for our final energy, the potential is 0. And we know from energy conservation that our initial energy, the initial energy of the ball, the whole system, has to be the same as the final energy. So we can equate these things. We can equate our initial energy, REI, with our final energy, EF. And this means that if we take our mgh here for REI, this is equal to a half mv squared from the final energy, EF. So we're really just plugging in numbers here. So now we're getting somewhere. We have a term here containing our h, which is what we want, and we can divide these m's out because they're on both sides. So we just divide through by m, and now we have gh equals half v squared. And we know our g is just a gravitational constant, and we know our v squared, it's 10 meters per second. So we can rearrange this to get h equals 1 over 2 v squared, and then I'm just going to move this g underneath the v squared, so v squared over g. And this is our expression for h. And now you can see we can use trigonometry to find our theta, because we now have a h, we have an L, and it's just a case of plugging in values. So if you remember from trigonometry, the sine of an angle, so in our case sine theta, is equal to the opposite, which is h, opposite of the angle is h, over the hypotenuse, which in this case is L. So we'll just put in our values for h. So we get the sine of theta is 1 over 2 v squared over g L. Let's move down here so I can see what I'm doing a little bit better. And now if we want to find theta, if we want to isolate theta, we just take the inverse sine of both of these sides. So the inverse sine over sine is just the interior of the sine, in this case theta. And now we have sine to the minus 1 over here, and this isn't 1 over sine, this is the same as arc sine or a sine or however you've seen this before. This is the inverse sine. So it's the inverse sine of 1 over 2 v squared over GL. And if we just put numbers in here, we get that this is equal to the sine, the inverse sine of 0.204, which gives us a final value of theta of roughly 12 degrees. And this is what we're looking for, this is our final answer. So you've gotten yourself an easy 5 marks there out of 25. And there's a couple of things to note about this question. So I started off by drawing a picture of the situation, and I really recommend you do this for pretty much any question that involves mechanics, because it turns out most of the time you're going to be dealing with something like this where it's a triangle, and maybe it's not so easy to see it just from reading the question, but when you draw the picture it becomes very obvious, and then you realize immediately you're looking for this h. In this case you're looking for the height. And a second thing, we used energy conservation here just because I personally prefer it, and I think it's much more useful to learn energy conservation laws. But there are other ways of doing this, and if you're more comfortable with equations of motion, you will get the same answer out in the end. And if you want me to try and do a video on that, I'd be happy to. But that's the end of the first question, and now let's move on to part B. So let me just clear myself some space here. And we're starting on part B. And let's see what we're dealing with. A typical Ferris wheel has a radius r equals 10 meters and rotates 2 times per minute. Find the magnitude of the acceleration experienced by a rider on the wheel and sketch the direction of the rider's velocity and acceleration. So, again, we're going to draw ourselves a picture, and this time we have a Ferris wheel and has a radius r equals 10 meters. And what else do we know about this? So we know that this Ferris wheel is rotating 2 times per minute. So the period of rotation, t, is equal to 30 seconds. And this will be important later. So what are we looking for here? We're looking for the acceleration experienced by a rider. Now, there's again a few ways you could do this, but I'm going to consider the force that the rider experiences because to me that's the simplest way. So let's think about the force experienced from circular motion, the centripetal force. This is the force on somebody who's sitting out here. So this is our rider. In fact, let's make this a little more personal. This is our rider on our Ferris wheel. And he's experiencing a force of m, his own mass, times v squared, the velocity that he's travelling forward at. So he's travelling in this direction. At v, this is perpendicular to our Ferris wheel, over r, where r is the radius of the Ferris wheel. And this is equal, from Newton's law, to ma, where a is the acceleration. This is what we're looking for. So immediately we can see we have something here that looks like what we're trying to get to. We can cancel these m's. I guess we have to put an m under here now. But now we have a equals v squared over r. So let's write this down. So great, right? We already have an expression for our a. The only problem is we don't know what our v squared is. But if you think about the fact that v is, this is distance per time squared times 1 over r, things should start to become a bit clearer now. Because in this case, the distance that we're travelling is one full rotation of the Ferris wheel. So this is actually 2 pi r, right? Because one full rotation of the Ferris wheel means you're going around a circumference of this circle. So that's a length of 2 pi r divided by the time it takes for one round trip, which we know is 30 seconds. This is our period. So great, we have an expression. Oops. Pardon me. We have an expression for our velocity. And then this is just multiplied by 1 over r, and the whole thing is squared up here. And if we just write this down a little bit more neatly, we have 4 pi squared over 30 squared multiplied by r, because our r here cancels with one of the r's from our r squared, so this isn't squared anymore. And now it's just a case of plugging in numbers. So let's put in our r as well. Our a is equal to 4 pi squared over 30 squared times 10, which is equal to 0.44, and this is meters per second squared, because we had meters up here for our r, so this is actually 10 meters, and this is 30 seconds squared. So we have 0.44 meters per second squared. This is an acceleration, and this is exactly what we're looking for to answer this question. And now all we need to do to finish this off is sketch the direction of the rider's velocity and acceleration. So we've already sketched the rider's velocity here. Up at the top we have a v from before, and the acceleration, this is another strength of using the force. The acceleration is obviously travelling in the same direction as the force because we have F equals ma, and these are both actually vectors, so we can put some arrows here and this is still equally as valid. And our centripetal force is always acting towards the centre of our circle, right? Because this guy wants to fly off in this direction, in the direction of his velocity, and the centripetal force is pulling him back towards his circle, towards his circular path. So our force is pulling him inwards, and our acceleration is travelling in the same direction as his force. So our A is just pulling him towards the centre of the circle. And that's it. That's the question finished with. That's another 5 marks. Not really much to note here, other than, again, there's different ways of doing this. You could use equations of motion again. You could even use energy again if you wanted to, but I thought it might be nice to move away from that and show you something different in this case. All you really need to remember here is that the force of any object on a circular path, the force acting on any object on a circular path, is mv squared over r. And then from there we just remembered Newton's laws and basically rearranged. This is all just algebra to get to our final answer. And now, with that done, let's move on to question C. I'll make myself some more space down here. So we're on our final question now. And this one comes with its own picture, which is nice. And it tells us a ball rolls along the frictionless track shown in figure Q1, which is this here. Each segment of the track is straight, and the ball passes smoothly from one segment to the next without leaving the track. Draw 3 vertically stacked graphs showing acceleration a, velocity v, and position s versus time t. Each graph should have the same time axis. Okay, let's get started. So we're on question C. And I'm going to draw this picture again so that we can stack our graphs against it. So we have a track that looks like this. Let's make this nice and long. So it goes down like this, and then we have kind of a shallow rise here, and then it's just a constant onwards. Oh dear, that is not very constant. Let's try again. And then we have a constant flat line here. Use your imagination. And our ball starts from up here and it's going to move along this track, so it's going to roll down here. It's going to come here and slow down as it rolls up here, and then a nice constant speed here. So our first graph, let's start with acceleration. We have our acceleration here. This is our acceleration axis, and A is our acceleration in this case. And we have our time axis in this direction. So this is time t. And all we have to do is consider our track. So how is this ball going to accelerate? So for the first section of the track, we just have a linear ramp, which means that the force on this ball is constant. And remember that F equals ma. M is a constant, F is a constant, the force is constant here, there's nothing changing here. So A is also a constant, which means that our A is just a line along here, just a single value, until it hits this change in the track, and it says here that our ball passes smoothly from one segment to the next. So there's no bouncing here, there's nothing happening, it's just moving. It's rolling here and it's rolling there. So our acceleration immediately changes once it hits this transition. And now it's rolling upwards, right? It's the same thing as before, but it's now upwards. We have a straight track. So our force is again constant, only now it's pushing this way, which means our acceleration is constant, but our acceleration is negative because it's rolling, it's trying to push the ball in the opposite direction, although the ball is still rolling forward. So again we have a constant A up to our transition point, where the ball hits this flat piece of track, and now there's no force. Our force is 0, so our acceleration also has to be 0. So we just move up here. Our acceleration is now constant and it's 0, so it's along the axis. So it just follows the axis like this. Oops. And that's it. That's our acceleration graph drawn up for us. And now we can move on to velocity. So we're going to follow the same motif. We have our velocity axis here, and our time axis comes out here, and it wants the same time for each one, so we'll make this roughly the same length. And let's think about a relation between acceleration and velocity. So we have velocity is equal to acceleration times time plus some constant. So what does this mean? This means that if we have a constant a constant acceleration, we're just going to have a times t plus some constant, which is arbitrary. Which means that for any constant a, our velocity is linear. So this is just an upwards line as we move along t. Oops. Let's put our t here. So this is just a nice constant line. And then we hit our transition. And again we have a constant a, but now it's negative. So now we just have a times t with our velocity now decreasing because our acceleration is negative. It's trying to push the ball back this way. It's rolling more slowly as it goes up here. So we have a positive increase in velocity, and then we have a decrease in velocity, and then finally we hit this flat piece of track with no acceleration, no force is acting on this. So our AT is 0, and now we're just left with our constant. So V is just a constant in this case. And so we have just a flat line on our graph. And what's interesting here is that our velocity actually looks kind of like the inverse of our track, right? If you just flip our track upside down, we have a velocity graph. I just think that's a nice thing to take note of. But that's our velocity graph done. So now let's move on to our position graph. So again, we're using roughly the same time axis. I apologize for my drawings, by the way. As I said, I'm new at this. So we have position going up this way, and then time coming out here. And now again, let's think of a relation between velocity and position in this case. So we want s position equals, and it's exactly the same thing. It's vt, velocity times time, plus some constant c. So let's assume our constant c starts at 0. Our ball starts at 0, and our position is moving in this way. So this is actually our s, as the ball rolls along here. So we have s equals vt, and our v is now linearly increasing, so our s is going to be parabolic because we effectively have s equals at squared plus c. So let's draw that. We have a parabolic increase like this up until the transition point, and then our v is now linearly decreasing. So again we have a parabolic curve, but now it's going to decrease. But our velocity never goes negative, so our change in position with respect to time is never negative either. So it never moves back down, it's never rolling back along the track in the opposite direction. So it's just going to do this up until this transition onto a flat piece of track. And then our velocity is a constant, our position is just v times t. So this is now just a nice linear increase. There's no parabolic curves. Oh wow, I am sorry for these graphs, but you get the picture. And this is everything that the question asks for. We have our three graphs, they're all stacked. And you can clearly see the relation between acceleration, velocity, and position. So there's not really a lot to note here. You don't have to write these things next to the graphs. You don't have to write f equals ma, for example. You could just sort of deduce this just from looking at the track. But I think it makes things easier, it makes things a little bit more intuitive, so you see what's happening. And that's 5 marks per graph, so 50 marks in total, and then you're finished with the entire question. And you've got 25 marks. And I think this is a really nice example of how to tackle a lot of different and interesting mechanical concepts quite easily using very simple methods. So we started off with our ball rolling down a track and used our energy equations, our energy conservation, and then we moved on to our man on a Ferris wheel and the forces they experienced. And then we finished off with just some nice relationships between acceleration, velocity, and position. I hope this video helped you guys. If you liked it, please let me know. Please leave a comment. If you want more, feel free to ask for any other subject that you might be interested in, preferably within physics, because that's basically all that I know. But that's the whole question. We're finished, so thanks for watching and see you next time.